All right. Good morning, everybody. Uh, I am Colin Tam, Chairman of HAESCO, the Hong Kong Energy Services Company, and the moderator for today. First of all, and on behalf of HAESCO, it is my honor and pleasure to welcome you all to the fourth 2021 seminar of the HAESCO OSI Energy Efficiency Forum. We have one of our three speakers here, and the meeting is meeting organizing team led by Mr. Rob Chen and Ms. Amanda Shun are physically here in the Polytechnic University site to help organize this event. We also have an audience online. Two of our speakers will speak from Beijing and Singapore. Now, before I go any further, I want to thank all the audience to our seminars, whether you are physically with us or online. I hope that all of you will find your time well spent this morning. I would like to introduce some of our board members who are with us here today. I would like to recognize our honorary secretary, Dr. Ivan Lee. They were just behind me, and also Mr. Sampson. There are other board members probably online as well. Our honorary chairman, Dominic Yin, have other engagement this morning, so he won't be able to join us today. During the past 3-4 years, HAESCO has organized every year at least 4 professional seminars, an annual conference on specific topic of current interest, and for the last 2 years, it was hydrogen economy that drew several hundred audience from all over the world. HAESCO also sponsor factory visit in the Great Bay Area and support the 2 most important environmental conferences and exhibitions in the Great Bay Area. The ECHO Expo Asia Conference in Hong Kong and the MIECF Conference in Macau. Ever since the inception of ECHO Expo Asia, HAESCO is a supporting organization of these largest environmental conference and exhibitions, and its chairman has served as a member of the task force that plans the event. As a result, HAESCO was able to secure booths in both of these events free of charge for the users of its members. If you want to become a member of HAESCO, we have application form here, and you can talk to Miss Amanda Shen. Alternatively, you can also visit our website and fill out the application there. Your trial membership will be free until end of 2022 if you sign up before the end of the year. So you still get the 20 some odd days to take advantage of this offer. The seminar is funded by the Clean Production Partnership Program, CPPP, of the Hong Kong Productivity Council, HKPC. Topic of discussion for today is the state and trend of smart grid in manufacturing industry. We all know that the internet and the artificial intelligence and the 5G is now dominating everything in our life. So that this topic is truly timing and very useful. The Hong Kong Polytechnic University is also a co-organizer of today's event, and the supporting organization are many, and they were listed in our flyer. For those of you who have registered for today's event, you probably have seen them there, their logo there. And I, on behalf of HAESCO, want to thank all of them for the support of this event today. Without further ado, our first speaker today will be Dr. Harry Ni, who will talk about achieving the 30-60 targets, the 2 carbon targets set by President Xi Jinping in terms of the new power systems and the cloud-based virtual power plant, VPP. Dr. Harry Ni is the founder and board director of EnerCloud Asia Pacific, an innovative integrated virtual power plant company. He also served as Senior VP of QU, Creative Technology Company Limited in Beijing, QCTC, which is a leading smart grid IT solution provider in China. Harry started his career at PJM Interconnection, one of the largest nationwide interconnected power network in the US in 2002 after his PhD degree. He is responsible for the power market dispatch, transition management, smart grid R&D, and its related applications. As technical director, he also won the 2010 President's Award in PJM interconnections. In year 2012, Dr. Ni joined Accenture as Senior Director of Smart Grid for the Asia Pacific region. He led his team to provide high quality consulting and IT system services to more than 30 Chinese power grid utilities and 10 plus power generation companies. With the end-to-end solution on VPP dispatch, on electricity and carbon trading market, on smart power plants, and aggregated energy services, also with energy IoT, etc. Dr. Ni received his PhD degree in electrical engineering from the Arizona University in 2002 in the US. Harry, the floor is yours.
Okay. Thank you very much, Colin. And really appreciate HAESCO's invitation to give this speech this morning and to share whatever some of the observations I got when China is pursuing its 30-60 decarbonization target. So this maybe I should share my let me see. I have some PPT to share with you guys. Let me see, where is it? Okay. Can you see this my screen?
Yeah, yes, thank you.
Okay. Okay, thank you. Okay. Good morning, everyone. My name is Harry Ni, and really glad to take this opportunity to share some of our observations in Chinese market reform and the latest the pressure and and also the increasingly the increasingly kind of the some technologies that already got increasing attention from state level to local department level, the local government level, and which is the virtual power plant. So I will start my this is a disclaimer, and I will actually give you these 4 parts of the introduction. I'll start with the background and then share with you some of the experience in the Chinese power market, especially at provincial levels, spot market pilots, and then I will share with you from the Department of Energy and NDRC level, what kind of the new so-called new power system and new market mechanism are necessary for to achieve the 3060 targets. And the last is the introduction of the one of the VPP technology, which is the Ener cloud-based VPP. And you can see the carbon neutralization is becoming a global consensus, and this is really just the statistics or picture to show you how large in this world all the countries pretty much reach consensus to to achieve the decarbonized economy, and in order to face the challenge of the climate change. So like the economist said, in September 22nd, 2020, President Xi actually basically put forward that China will enhance the state's independent contribution to adopt more effective policies and measures, and the CO2 emissions will strive to peak before 2030 and also achieve carbon neutralization by 2060. That's where the 3060 so-called targets were first officially mentioned by the President Xi. And then in early this year, President Xi basically would try to, that in one of his central committee meeting on the finance and economics, and he proposed the solution to achieve these 3060 targets, and which is to regulate the total amount of fossil energy, striving to improve utilization efficiency, implementing renewable energy substitution actions, executing power system or power market reform, and build a new power system with new renewable energy as the main sources. So that's the first time the new power system is brought out to as a solution, even though it's still a very widely defined, it's still kind of the not clearly defined concept, but this is a new power system is what President Xi proposed to achieve the very aggressive 3060 targets. So in order to understand the 3060 targets and the relationship with the new power system, this is this slide is what we try to explain the relationship. To achieve the 3060 targets, actually there's 3 big area of the requirements. Number 1 is decarbonized and the diversified supply. Secondly is a reliable system and safe operation. And third one is innovative and pragmatic regime and regulation. So you can see that from the supply side, demand side, and also from the power system side, all need to improve and significantly from the efficiency level, from the security level, and also from the so-called like the diversified level. So to understand these four requirements, we further can split into four areas that we need a lot of work. Number one is a friendly and efficient integration. That's not only means the refers to the renewable energy, but also the diversified flexible resources from the demand side level. Okay, so for example, from the EVs, from the heater, from the all the transportation level, and also the smart building level side. So all kind of resources, as long as they can help the decarbonization, they can help the nation state level to achieve the 30-60 targets. That should be a friendly and efficiently integrated into the system, power system. And also the second characteristics to the new power system is high resilience. And that's basically means the whenever we all know that the new power system will have the high penetration of renewable energy, and so with all this high penetration of renewable energy, their uncertainty and their uncertainty will they basically hurt the whole grid from time to time. So we need the grid operation to be resilient, to be flexible enough in order to face the challenge from all the renewables like the solar and the wind. And that's why we believe the virtual power plant is expected to improve the system the grid operations capacity and also the resilience. So that's why right now from the statewide level to most of the Chinese provinces, power utilities and also a lot of investors are trying to are kind of building VPP pilot, or are working on the VPP planning in order to achieve the like I said to reach the high resilience, to help the grid power system to become high resilient. And also the third characteristics of the new power system is digital transformation, and that's really easy to understand. So digital transformation definitely will improve the efficiency of not only the communication but also the control of all the resources connected to the network. And the third one will be the market mechanism, effective market mechanism. So that's pretty much kick off by this second round of the Chinese power market reform. But this kind of the getting more and more kind of pressure to by the central government to force all the market participants should compete fairly, or should be treated fairly, and they can compete openly and fairly in the new power market. And that's why the central government believe this reform, this type of power market would help to reduce the system cost while optimize the while they optimize the grid operation, and meanwhile still keep the system under the very secured and safe level. So that's the so you can see the new power system actually contains four characteristics, and I repeat just once more, is the friendly and efficient integration, high resilience, digital transformation, and effective market mechanism. And in today's session, I may focus on the focus on the VPP, which is falls under the first two characteristics. And also I will also mention what happening in this round of Chinese power market reform, and what lessons we learned, what experience we also got from the pilots. So so you can see this round of the Chinese electricity market reform is actually kick off by the NDRC and DOE in 2015. It follows the number 9 document issued by the State Council officially, and on March 15 of 2015. And once after the number 9 document issue, and all the Chinese provinces actually, the local government actually start working, some faster, some slower, but they all kind of start working on the reform of their local power market, and that's actually they all follow the number 9 documents required. That means the deregulated wholesale electricity market, the long-term contract trading market, and then the ancillary service market. Since 2015, they have been working on that for 6 years to build up all these type of markets, even though they're still in the middle of the road, but they are working on that very hard on that. And since almost all provinces start from the building the long-term contract trading market, a bilateral market, or the contract, or the OTC market. They found they cannot move on even further without a spot market, because without spot market price signals, is really hard for the market participants to select to make the deal from not only from the supply side but also from the demand side, and that's why in 2017, also urged by the NDRC and the Department of Energy, 8 provinces were selected as the pioneers for the spot market pilot. And so they start. They took the task to try to set up this spot market for each province, and also to check if that spot price, the pricing mechanism, can be really set up. So, and that means we can get the good price signals from the spot market, and that's what happened since 2017, and starting from 2019, almost all these 6 provinces all formally kick off their spot market, and they still call it as a trial runs, but they all kick off their trial operation, and so start from the 2 years ago, we can see the spot market price from these 8 provinces, and also gave the power industry a lot of interesting information, and also the deeper understanding on how the electricity, how the supply and demand can meet each other from the daily point of view. So that's what happened. That what happened in these 8 provinces. So you can see these 8 provinces. I have this table to show you to compare these 8 provinces, because since in China, actually all these 8 provinces have their own they're all kind of so diversified. They all have their own kind of the different industry, and also the power supply structures. So actually also some of them are really rich in the renewables, but others many need the power supply from outside or from neighbors. So they all have their own understanding on this spot market. That's why they have their own, they chose their own market model. and also have the different market rules if you look into the details. And this is a table to compare them. But you don't have to read them all, but just want to let you know among all these 8 provinces, right now 7 of them, actually 6 of them, are follow the US market model, or US market model, which is pretty much centralized, so-called centralized smart market. And in Inner Mongolia and the Fujian, they follow a different track. They follow the UK model. Okay, they build up their smart market as the from the pretty much similar to UK. What the UK power market is doing now. So we call this kind of the basically that kind of the this pretty much like the diversified market model. So this different market model means what? Means the long-term bilateral contract will be physically executed or not. So if in the centralized power market, because all in the spot market, all the power or all the supply and the demand side all will be bid in and cleared together. So the long-term energy contract by for example by supply and demand side, they mainly honored from the settlement point of view instead of like the physical execution point of view. But in the Mongolia and the Fujian, if once the supplier and if there's a one if there's a bilateral contract, long-term contract signed to, for example 3 or 4 months ago, and that will be honored and executed during the operation day. So that's a major difference between these 2 type of the market models. And so, but among all these 8 provinces, other than the market model difference, and one main difference is right now they are all one side, almost all are one side kind of market, which means only the supply side generation power generation side can bid in and cleared, and the consumer or customer side demand side actually they cannot bid, they would not bid in to clear the day ahead market or the real-time market. And so that the customer side still not explicitly participate into the market, but because in each provinces the local utilities use the demand, use so-called like a demand forecast curve to replace or to on behalf of all the customers. So the price still somehow represent the true value or real value of electricity when they physically deliver. So that's even though that's not 100% follow the so-called theoretical model of a spot market, but that's still what we can see, what we can tell is the close to the ideal model. Okay, so that's the 2 messages I want to share with you. And like I said, since 2019, after more than 2 years on and off operation, I mean the spot market operation, we have gained some valuable experience running smart market at provincial level, and also learned quite a few lessons. And some observations are kind of listed below. And they are right now the main concern or main problems for all these Chinese power markets. And they all are kind of working out different solutions to resolve those problems. Number one is what we observed is the imbalance of settlement payment. So that's actually really naturally come from from the Chinese so-called like dual track pricing system. So as we all know, before the market reform, Chinese electricity industry is actually a planned economy. It's a product of a planned economy. and so that the quite all the generation and all the generation basically all kind of stayed on, and they all follow the same price, their own price. Each power plant follow a certain kind of fixed rate to deliver power into the grid, and also grid will sell those electricity to the consumer by following the so-called like the listing price, kind of also a fixed rate by the local government. So you can tell that the pricing mechanism before the market reform, they pretty much determined long time ago, and by the government, and actually are fixed rate, even though later on Chinese government introduced so-called like the so-called like the peak hour rate or something like that, but this is still a very limited level, okay, very limited amount of the power electricity consumers can tell the difference between the 1 kilowatt hour used in the morning or in the evening, and any different, they cannot tell any difference because the price is all the same. So due to after the market reform, about like the 70% of the coal-fired plants are pushed into to participate into the power market. So they have to compete with each other. But remember, there's only 70% of the coal-fired plant. But others like the nuclear plants, renewables, and some gas-fired plants, and are not allowed to participate into the market. So you can tell from the supply side, only part of the power plants are market plants, okay, market resources. They can compete, they will compete freely with each other. But the others are still follow the pricing or follow the same rate pricing determined by the government. And the similar thing happened on the demand side. Is the demand side also only part of the for example, large industry customers and or commercial customers, they are allowed to participate into the market, and they will get bill follow the market price. But others still, for others and remaining of the customers still follow so-called listing price, like I said, determined long time ago by the government, local government. So due to this dual tracking pricing system, and you can easily tell, because the demand really the demand from the so-called like the market customers and on-market customers, because they can move daily and even hourly, and we cannot be sure in every hour the market demand equal to the market supply, right? So that's why when you do the settlements, you easily can see the imbalance. So that's the number one observation, and also the critical problem we observed after we only partially open or reform the market. And the good news is just about like 1 month ago, the central government and NDRC just issued a new order called 1439 order, and that order actually asked all the customers, I mean all the demand side, all the customers has to participate into the power market. The only exception would be those kind of the residential customers, but they are very kind of a tiny part of the whole electricity consumption, so that should be okay. And on the supply side, and all the coal-fired plant will be forced to participate into the power market. And also, according to the strategy, according to the plan, all the on the renewables and the especially newly set up the renewables and gas-fired plants and eventually nuclear plants, they all will attend the market. So you can see within next 2 years, we can see more than like 80% of the supply side power supply, and more than 90% of the demand side will all participate into the market. That will really going to help this market not only from the kind of the market, the cash flow point of view, but also help the market to really to can find the right real value of the electricity. That's number one observation. And also you can see the one observation is about like the unequal treatment of renewable and traditional power resource. So in most of the provinces, renewables are not allowed to participate into the market. And just because the central government right now really want all the renewables to be 100% accepted by the grid. So that means no matter how much power generated by renewables, and no matter when it's generated, the grid has to accept them, buy them, okay, into the grid. But you know that's not the that will cause some problems when we run the market or run the power system. So that's why like I said, in the order of the 14 the renewables will eventually participate into the market. But however, but because of the 30-60 targets, the renewables still they are green. So that's why they have to be their priority wise, they will be taken by the grid at high kind of priority. So that that's why we need more flexibility from the demand side, okay, from demand side. And the third observation is like I said, because the power consumers are not allowed to bid into the daily market, daily spot market. So the pricing, the day ahead and the real time market price will not really kind of represent their own will. Okay, they want to do, maybe they want to bid at a higher price, but the clearing price at the end would be not what they expected. But doesn't matter. Actually, we can see that means that's only we are still in the middle of the road to the spot market. So most of provinces, some provinces like Shandong and Shandong is already kind of the other side. I mean, to the demand side, so that allow the power consumers to bid, just like the generation side, to bid in the day ahead market, so that they can both sides can bid into the market and form a to achieve the balanced the day ahead market price. And okay, so that's what's going on now. And also you can see ancillary service market is really critical. Like we said, in order to get more renewables into the market. The reason is you can easily see the dark curve in Shandong, in Zhejiang, and just like we observed in California, because due to the solar power kind of really high penetration during the day, and you can see the valley hours happened pretty much starting from the noon to the 3 p.m. So that's why and really that hurt a lot of coal-fired plants, because they may have to force to generate at minimum level, and even worse, they have to turn off their plant. So that's really bad. And so that's why we really need ancillary service to help that. And that's why when we see and that's why also we see demand side can make the great contribution or great potential to help that problem. And also the one last one on the table, but not the last one on the list, is insufficient reserves and insufficient flexible dispatchable resources, and due to this increasing penetration rate of renewables. Just like I said, due to in order to achieve 30-60 targets, and coal-fired plant, their online hours continuously decreased, and all the state-owned SOE generation groups, they all they start selling and all of the closing their some of their low profitable coal-fired plants, and that will continue. Okay, continue. And according to the a research from the environmental protection group, by 2050, there will be only like the 15% of the coal-fired plant will still left in the Chinese market, and so that you can see they will really going away. But due from now to 2050, we still need those plants, but we need to find a way to help them to survive. Not only just to help them to survive, but also to explore their potential value, which means they can provide the capacity if when the system really, when the power grid or market really need it. And and that we can see in either this in 2021's winter season, and also in last 3 months, we can see you already heard a lot of the power shortage in China, and at that time they have to rerun some coal-fired power plants to meet the challenge. Okay, to actually to face the conquer the shortage issue. But so you can see during this from now to the transition period, during this transition period, coal-fired plants we still need them, and if we have a practical capacity market mechanism, they will be able to get some. They will be able to survive. That's according to our research, and also they will help the Chinese government Chinese 30/60 targets to be achieved without with more comfort instead of like a painful the experience. So that's what I share with you what happened in the Chinese in this round of Chinese market reform, and also the what happened in or what we observed from the provincial level spot market pilots. And then, so you can tell from the right now, I just let you know the second round of not second round, actually more provinces will start this spot market, and in next 2 years. So it's planned like by 2023, all the Chinese provinces will run the spot market, and will run the ancillary service market, and also will have some type of the energy so-called capacity market. So you will see that in next 2 years, China at the provincial level, you will see the even a brand new, even still the young, but it's somehow like the complete power market structure or mechanism in China, in Chinese provinces, and also so that on the road to this to the market reforms. So you can see Chinese power industry has to meet the 2 goals. One is the 30/60 targets set by by the central government and the highest level, and also they have to complete their market reform, or make them to be to match the market reforms requirements. So new power system and new market mechanism both become the driving forces to all the power companies, and also triggered, also bring a lot of opportunities and a great potential to the not only to the IoT industry, to the innovative technology technology companies. So that's why we have today's session to share with you what happened in the market reform, and also the 30/60 targets together. So energy IoT will base the integrated high resilience power grid will be the next generation of smart grid and the core carrier of energy IoT. So that's its core advantages, including the high load-bearing capacity, high interactive technology, high self-healing mechanism, and extraordinary performance. So this right now, what I mentioned here is we are going to have this great platform which called new power system to allow all the new technology, especially the energy IoT based technology, to be able to plug into the power system and to attend or participate into the market to get the value, to find their right or the profitable business model. So that's what this slide will try to tell you. From the generation, grid, load, storage, all these different resources will work together to achieve this high resilience new power system. And especially I will mention these two. You can see in the picture in this slide, there are 4 beams and 8 columns, and 2 columns I want to I would want to emphasize. Number 1 is under the load. You can see the high resilience new power system it has to awake and aggregate a large amount of distributed resources together through the virtual power plant. So that's why it's VPP become such a hot topic in China, especially Chinese power industry. And also you can see the other one, the column is right behind, right kind of side of it is innovative market mechanism, because only we have the market mechanism can pretty much build up the environment to help the VPP to get revenue from the market, to make money, okay, from the market. So this technology and also the market mechanism, this innovative technology and the market mechanism, these two has to work closely together and in order to succeed. So that's why we mentioned this. We have this slide to share with you what the future Chinese new power system will be. And the VPP will allow, why we keep saying VPP, virtual power plant, is really not a new concept. Actually, it's I believe it's even brought up more than 20 years ago from US or European scholars. But this up to only until now in China, it's become really hard. The reason is they found, like I said in the previous slides, right now in order to achieve 3060, in order to face the challenge from the high penetration of renewables into the grid, and we feel like we will use all the resources, and not only from the generation side but also from demand side to meet this challenge, to work together to really to keep this, to make the system or grid to be sustainable and also the flexible. And that's and also in the last 30 or 40 years, most of the supply side, most of the resources from supply side, and basically we know very well, okay, and we already, some of them we use the values also very, we already recognize their values. But on the demand side, because of the our economy, because of the demand side have the all the become so different from even 5 or 10 years ago. We see a lot of more EVs. We see a lot of more distributed solars, or even the solars, and we see a lot of more kind of the for example, like the Teslas, like the Powerwall, like the distributed energy storage, and we also see a lot of the electricity devices in the family or in the commercial buildings. They become smart. So all this kind of all this gave us opportunity to revisit the potential from demand side. Okay, that's why the VPP, that's why the VPP at this moment really can play that critical role to integrate all the diversified and distributed resources together and as one big resource into to participate into the market. And so that this is really a structure on the map. Actually, we show with all the local utilities in China. We tell them that you can just open your mind to use distributed solars, EVs, or charging stations, air conditioners, water heater, and like I said, any other resources that can do the heating or cooling storage. They can do, for example, all these. They have the flexibility to turn on and off. All these kind of resources from demand side can be used. Okay, can be used by VPP. And once if they can integrate it into VPP, they can participate all the markets that traditional power markets, power plants can participate. For example, spot market, a long-term contract market, capacity market, and service market. And they will be able to participate in the market annually, quarterly, monthly, weekly, all the way down to daily. So and they will also enjoy the price or the revenue from the electricity price change and also the capacity price. And so that all this, so that VPP will become just like a new type of resources that can move on or move up and move down according to the market signals and freely and flexibly to help to give the grid operators more the power or more the options to face the challenge from high penetration of renewables. So and some provinces in China, local government in China already kind of they already kind of issue some policies, that the incentive policies, in order to encourage the VPP or VPP type of demand side resources to participate into the market. So I just give you some example. For example, in Shandong, you can see the Shandong, like for example, the market maximum capacity compensation price will be 2 yuan per kilowatt hour per month, and Zhejiang maximum subsidy for the peak shaving. Okay, sorry, I didn't put here, but for peak shaving activity, demand side resources could be 4 yuan per kilowatt hour, and also Guangdong, you can see even 4.5 yuan for kilowatt hour for peak shaving, and and also we can see the 0.12 yuan per kilowatt hour for valley filling. So you can see and more provinces will join this team group to encourage VPP type of demand side resources to participate in the market. And then with all this very good under these situations, that's why we share with you this cooling opportunity by the yeah, okay, I will check the time. So this cloud based VPP actually is trying to tackle the issue of two things. One is a lot of the cooling, kind of the space cooling energy are used in China, okay, and a lot of most of them are split units, but you can tell that all these resources right now are basically just the energy just used, and they just consume the power and without any contribution to the power to the grid. But you can tell, just if we only to consume the power, and by 2050 we may add 425 gigawatt of new generation just to meet that growth of the cooling requirement. Okay, why is okay, and you can see with the opportunity, like I mentioned above, well, from the electricity market reform, you can tell that that you can see from demand side resource, we can see like the mini split AC air conditioner market can just for the existing market, they have over 500 million units, and all of them add together, they will give us the tremendous amount of the capacity and flexibility to help the power market and help the power system to achieve to take more take into more new renewables and so that as to achieve the 30-60 targets. So that's just in the Zhejiang province. They have the plan to add 10,000 megawatt decade resources from the demand side, and also from the 5,000 megawatt real-time resources from the demand side. So all are not free. They will be paid, and if we use the tremendous amount of the existing resources from the just from the, like I said here, from the air conditioners split AC market side, we will get the surprisingly high revenue or the return from our investment. And so EnerCloud basically top partner with Flare to propose this VP virtual power VP model 01. Okay, propose this VP model 1 and to achieve the 3 targets. So number 1 is it will design for the mini splits, mobile, window, cassette, air conditioners, and that will be very easy to install for all the for every family. And also it can all, once after it's installed with this VP model 1, they will become the smart kind of the devices. They can be controlled by their the owners mobile phones, and will also be able to kind of integrate into the to be visible and controllable from the cloud, so-called. So they will be able to become a great potential for as the one integrated virtual power plant. So with the help of this VP Model 1, we'll be able to convert the traditional and even not so smart or traditional air conditioners, no matter smart or not, but convert them into the virtual power plants, and also partner with 3M to convert it into the air purifiers. And that all be kind of with the help from this plug model 01. And that will allow us to turn all the traditional AC or all type of AC into split AC, into the smart AC, and also to become air purifiers. And all this, if you take into account, like right now we are doing this, we are help the Hangzhou government to achieve this so-called, like they have this Asian game kind of the next year, and we basically want to achieve the 0 carbon emission during that 1 month of the big event, and so that we have this whole strategic plan for them. And we did some research that just in turn the Hangzhou city's residential level ACs into the virtual power plant, we will help the Hangzhou to become a 100% carbon 0 city. Okay, so that's really amazing. Okay, and really amazing to local government. And that you can, if you tell from the compare from the all this our solution to all the other investment into the so-called incremental resource or incremental carbon decarbonization solutions, you will tell the value really the cost and value really value to cost really high. So we will also turn the VP model 1 into the hub model 1 to allow these for more than 500 up to 500 VP models to link together. That pretty much means we are able to we are able to have the one or two big commercial buildings that can be clustered together into one virtual power plant. And so far one virtual power plant. So that one virtual power plant, like I said, they can not only contribute to the peak shaving and the value filling, but also can participate into the spot market and into the ancillary service market, and also the capacity market. And that's like I said in the previous slides, that's what really happening in most of the Chinese provinces, and also it's desired by the all the power, not only local government but also the grid operators. So that's why this solution we believe will be kind of will be great will be great support to the Chinese power market reform and also the new power system kind of the building. And some technical technology advantages will include this flexibility, like I said, of this of the Hub 01, and also is secure. All the data pretty much the encrypted, and also the data stays in China. Okay, Chinese all the data, Chinese customer data stays in China and will not be used by other countries or other players. And also it's already proved, we already through our pilots project in Guangdong already prove our demand side resources, this responsibility, and also the technical kind of the technical values. And also it has included in the cloud and in the server, we have this algorithm, machine learning algorithm to help residential users building energy managers and energy aggregators to maximum their profitability while keep all the ACs at a very comfort level, okay, to deliver its cooling at a very comfortable level. And also it's still customizable and for all different aggregate or energy energy managers and all different players if they want to use this solution. And all this basically are the kind of summarize our technical advantages of the cloud-based VPP. So with this the hardware and also the software behind and the machine learning algorithm behind, we'll be able to basically to partner with a lot of the we can find a lot of potential partners together right now with 3M and the others, and so that we can able to turn this smart hub, our cloud solution, into not only just a VPP, but also become also the very some smart devices for the to serve the whole family and the whole all the owners of those AC units. In addition to like the water heater and other devices will be added to the life cycle or to the on the board. So to summarize the value, you can see all air conditioning plus hot water plus the purifier will be in the energy cloud. We call it energy cloud is energy cloud, and that will help the grid aggregator to aggregate their consumers to help get value from markets, and also will help the property manager to better satisfy the customers' needs, residents or customers' needs, and to also to allow them to utilize the big data to help to better serve their customers, and also for the family, and they will get more comfort, and they will have the smart AC and water heater in order to better to make their life even better. So, and also save money from their contribution into the market and energy saving. So all this are on the energy cloud. So so that's pretty much what I want to share with you all friends online or offline today. And what I just want to summarize in order to achieve the 30-60 targets and to help the global climate change, and the Chinese government really desire for working on two things. One is one is the market reform, and to almost kind of the rebuild their market power electricity market, and to allow the all the flexible resources to be able to openly and fairly participate into the market and get the participate into the market. And secondly, also desire for innovative technologies, not only from the traditional supply side, but also from demand side. Especially the one example is the virtual power plant, like I said today, in order to help the new power system build up from both sides. So that's what I hope some messages I want to deliver to you people. And thanks again for the opportunity by HAESCO to giving the speech today. Thank you.
Harry, thank you very much for a very informative and interesting presentation. I still remember 40 years ago when I first graduated and worked for the American Electric Power. My job was to do transmission planning. And at that time, all we need to worry is how to dispatch on the supply side to optimize the marginal cost of of the grid, and
Right.
then participate in a coordination between the regions, like the PGM with ECAR, with the Western system,
Right.
and when I was doing my MBA thesis at that time of day race design is already a state of art things required, to do the course of service study, load study, and we are testing the big IBM 360 computer, mainframe computer capability.
Yeah.
And because low flow study will require overnight computing time to deliver the printout. So a lot of changes, right?
Yeah. Yeah.
Compared to what happened today. And I'm sure a lot of the audience will have a question for you. And I will ask them to hold it until the end of the seminar. We'll have a Q&A time.
Okay.
So thanks again, Harry. Please stay on
Thank you. Thank you,
and
Colin.
participate in the Q&A. Our second speaker will be Professor Xu Ying, who will talk about coordinated operation and planning of distributed energy resources, DERS, in the microgrid. He will be speaking to us from Singapore. So thank you for Professor Xu's participation in today. Dr. Xu received his BE, Bachelor Engineering, and ME, Master Engineering degree from South China University of Technology in Guangzhou, China in 2008 and 2011. And his PhD degrees from the University of Newcastle in Newcastle, Australia in 2013, or in electrical engineering. He is now an assistant professor at NTU, Singapore. He's also a cluster director at the Energy Research Institute at NTU. And prior to NTU, he held the University of Sydney postdoctoral fellowship in Australia. Now, between 2009 and 2011, he was with the Hong Kong Polytechnic University. And in 2015 to 2016, he was with the Electric Power Research Institute of China's Southern Grid. Dr. Xu published 105 SEI indexed journal papers, which included 65 in IEEE transactions and 23 in IET journals. That tells you how active Dr. Xu is in his research work and how hard he worked on publishing his results. I only, in my whole career, managed to be a co-author of one IEEE transactions, and that's already a lot of work. So congratulations, Dr. Xu, for your achievement here. He also presented over 50 international conference papers, 6 of which are held over 50 international conference paper, 6 of which are listed as the Web of Science highly cited paper. So a lot of people have read his paper and find it very useful. He also received 7 paper contest award and conference best paper award from IEEE and IET. His research outcome also have been practically applied by power utilities in Australia, USA, Hong Kong, Macau, and China mainland. So Dr. Xu is truly an international scholar. Without further ado, I will turn the microphone to Dr. Xu to talk about the coordinated operations and planning of the distributed energy resources. Dr. Xu, all yours.
Okay, thank you. Thank you, Chairman, for your kind introduction. So let me share my screen. Can you see my screen now?
Yes, thank you.
Okay. Okay, good morning, everybody. Nice to meet you online. My name is Yan, speaking from Singapore. It is my great pleasure today to join this event and share some of our research works on the topic of distributed energy resources in microgrids. Okay, so first of all, this is an outline of my presentation today. I will firstly give you a general introduction to a microgrid demonstration project in Singapore, which is called REITs. And after that, along with the time scale of the microgrid problem, I will introduce our research works on the operation of the DER, as well as the planning of the DER. So for the operation, basically we'll talk about the energy dispatch and the voltage regulation of the microgrids. And for the planning, I will basically talk about the sizing and siting of different distributed energy resources, including the distributed generator units, as well as the energy storage systems in the microgrid. Okay, so first of all, let me briefly introduce ongoing microgrid demonstration project in Singapore, which is called REITs, stands for Renewable Energy Integration Demonstrator Singapore. So since 2015, this project has been started since 2015, about 6 years ago. The objective of this project is to develop a research and development platform which can testbed and demonstrate the DER and the microgrid technologies, and also promote these technologies to Southeast Asia countries. And as you know, Singapore is an island city country, which is even smaller than Hong Kong, from east to west, 40 kilometers, from north to south, 30 kilometers. And this is our university, which is located in the far west of the country. And in this island, which is called Semico Island, we have this REITs project. So we totally have about 64,000 square meters to build up this project. And the whole project was funded and supported by government agencies, including the EDB, Energy Market Authority, EMA, as well as National Research Foundation, NRF. And we have about more than 20 industry collaborators which invest and operate the microgrid system in this island. You can see a lot of big names as well as some startup companies in this slide. Okay, so this is a roadmap and framework of the whole microgrid system. Generally speaking, we are going to build a total of 8 sub-microgrids, which can operate together as well as a networked microgrid system. In terms of the generation resources, we have a mix of diesel generators renewable energy resources, including the solar power, marine renewable, as well as the wind power. Actually, in Singapore, we don't have large-scale wind resources because we are located in the equator of the Earth. We don't have wind resource. So this wind turbine is actually for research of the low-speed wind turbine. And in terms of the energy storage system, we have a mix of batteries, including the Li-ion batteries, redox batteries, as well as a supercapacitor, flywheel, and we even have power-to-gas devices. And for the loads, we have the on-island industry loads, as well as load simulators, which can be programmed for research and test bedding. So for the first phase, 4 independent microgrids have been already built. Each has a capacity of 500 kilowatt to 1 megawatt. And in the second phase, we are now building another 4 microgrids in a cluster configuration. The capacity is relatively lower, ranging from 100 kilowatt to 250 kilowatt each. So all of the 8 microgrids are interconnected as a whole, so-called networked microgrid system. And they can be either connected to the main grid or can be islanded from the microgrid. Okay, as I mentioned earlier, this is an industry standard project. So different companies are investing and operating as well as collaborating with us for the whole microgrid research problems. So you can see that different companies are investing in different dimensions. So for my research group, I'm basically collaborating with Rolls-Royce Electrical Department to develop the microgrid controllers. And you can see other companies, they are doing research in terms of the energy storage devices, as well as the renewable energy generators, such as the solar PV, low-speed wind turbine, etc. So if you're interested, you can visit this website to have more information about this project. Well, this is the electrical structure of the whole networked microgrid system. You can see that we have a total of 8 sub-microgrids. At our university, we are actually operating the Microgrid 0, and some other companies like Rolls-Royce, EDF Front Lab, they are operating other microgrids. So all of the microgrids are interconnected through this 6.6 kilowatt linkage bus and operated as a whole. Also, it can connect to the main grid for the grid operation as well as islanded operation. Okay, some more on-site pictures. This is the so-called low-speed wind turbine I mentioned earlier. Actually, this is the first or the largest wind turbine in the whole country. As I mentioned, we don't have wind resource in this place. And this is a diesel tank. This is a meeting room. This is so-called double glass solar panel. Okay, so this renewable energy integrated demonstrator project is actually a comprehensive platform for us to do research and development, as well as demonstration and test bedding. So in my research group, we are mainly focusing on the system level coordination of the DERs in the microgrid. So this is a general framework of our research. So at the physical layer, we are basically considering 3 types of the DERs, including the flexible load, which can respond to the utilities control signal, and the energy storage system, including the electrical energy storage, as well as the thermal energy storage, and the distributed generators, including renewable energy based, such as the solar and wind power, as well as non-renewable based, that is dispatchable distributed generator resources, including the micro turbine, combined cooling heating plant power unit. Well, for the specific research problems, we are covering the whole spectrum of the microgrid control, operation, and the planning. So in terms of the control, we are actually looking at the frequency and voltage control from the primary to the secondary control level, ranging from the milliseconds to the seconds level. And for the operation, we are looking at the energy dispatch as well as the voltage regulation, which is also called tertiary control. And this operation problem ranges from minutes to several hours time interval. While for the planning of the DR resources, the problem is to optimally size and site the DER units in the microgrid. So we are looking at the relatively longer time scale, ranging from years to even decades. So actually today my topic is mainly focused on the operation and the planning side of the DERs. Well, for the specific methodologies, in terms of the control, we are developing coordinated controllers, including the centralized control, decentralized control, as well as the distributed control. And in order to verify the controller's performance, we also did some hardware in the loop simulation test to real-time validate the performance of the controllers. While for the operation and the planning, basically they are can be modeled as optimization problems. And the major difficulty there is the operational uncertainties from the renewable energy resources, such as the wind and solar power. They are fluctuating from time to time in terms of the power output. So we need to use optimization technologies that can address these uncertainties. So specifically, we are developing robust optimization, stochastic optimization technologies that can address these uncertainties problems. And besides, we have also designed some distributed optimization, which does not need a centralized agent to coordinate the whole system. And we also proposed a hybrid optimization methodology, which combines the advantages of robust optimization and the stochastic optimization. So this is a general framework of our research group. And next, I will briefly introduce each of our representative work in operation and planning of the microgrid. So I will start from the operation of the DERs. As I mentioned, the operation problem actually consists of two sub-problems. One is the energy dispatch, that is to dispatch the active power resources, such as the microturbine, energy storage system, as well as the demand response. And the second problem is on the voltage regulation problem, which is to dispatch the reactive power resources, such as the capacitor banks, the unload tap changers of the transformers, as well as the solar PV power converters. Because we know that the solar power converter actually is a power electronics device, they can also provide very fast and flexible reactive power into the grid. So the idea here is to also utilize these power solar PV inverters to provide voltage regulation support. Okay, so for the operation of the DERs, basically the whole problem can be modeled as the optimization problem. So we have the controllable variables, which I have mentioned here, including the active power resources, reactive power resources. Then we have our parameters, including the load demand, the renewable power output, as well as the electricity price, the network topology, and the parameters. So this load, renewable power output, as well as the electricity price, they can be stochastic parameters. So we need to do the prediction ahead. However, the prediction cannot be 100% accurate, which means we usually have the prediction errors. And this type of error is actually the operational uncertainties. So when we optimize these control variables, we need to consider these uncertain parameters into the picture. And besides, to model the whole microgrid, we need to have the power flow model. Traditionally, the power flow model is a highly nonlinear, convex model. So in order for the sake of the optimization, we need to design some linearized or tractable model for the power flow. And besides, we have state variables, including the voltage magnitudes of different buses, the power flow of different branches, as well as the power exchange between the microgrid and the main grid. So this is the general problem description for the operation. Then, as I mentioned earlier, the biggest challenge to the operation of the microgrid is actually the uncertainties from the renewable energy resources, as well as the low demand. Well, in order to address these uncertainties, in our research group, we have developed a series of so-called two-stage coordinated operation approaches. The principle is that we want to coordinate different DERs in different time scales based on their different characteristics as well as the responding speed. For example, the wind and the solar power, they can fluctuate very fast within, let's say, 10 minutes or even 5 minutes. So the traditional resources may not be fast enough to respond to them. However, for other DR resources, let's say the energy storage system, they have a much faster responding speed. So it's sensible to divide these DERs into different groups. Then we respectively dispatch them and coordinate them as a whole to manage the operational uncertainties. So in this figure, you can see the general principle of the so-called coordinated approach. So basically we have two stages. For the first stage, we dispatch the relatively slower responding DR units in a relatively longer time scale, let's say from hours to even to a day ahead. And in the second stage, we dispatch the faster responding or more flexible DRs within a shorter time scale, ranging from 15 minutes to hourly ahead. So the two stages are coordinated through a so-called a two-stage optimization model. Then for practical implementation, as well as the first stage decisions are optimized, they will be directly implemented before the uncertainty realizes. And this so-called first stage decisions will stay there until the second stage. Then for the second stage, as long as the uncertainties are gradually realized, which means that we can further improve our prediction of the uncertain variables with a relatively shorter lead time. So we can re-optimize the second stage decisions to compensate the first stage. Okay, so in this case, the second stage is also called recourse actions. So to summarize, the two stages are actually coordinated at different time scales towards the same objective, that is to maximize the total benefit or minimize the total operation cost of the full microgrid, considering the uncertainties. And to specifically, in terms of the optimization algorithms, in order to address these uncertainties, basically we have two types of the optimization technologies. Number one is relatively more traditional, which is called stochastic programming. So for this method, we model the uncertain variables based on their probability distribution function, PDF for short. So the input of this algorithm is a point prediction of the uncertain variable. Let's say the renewable power output, the low demand electricity price in terms of the point forecasting. Then based on this point forecasting, we will sample randomly the different scenarios based on their PDF. And then the whole optimization model is actually to minimize under the or maximize under the expectation of these different scenarios. Okay, so advantage of this traditional approach is a relatively simpler formulation and solution process. However, in order to model the uncertain parameter, we do need is probability distribution function, which is, however, not easy to obtain in practice. And another maybe shortcoming of this stochastic programming is that because we are optimizing under the expectation, so basically we can only achieve a probabilistic guarantee of the constraints satisfaction. So this is a principle for stochastic programming. But recent years, more and more people are actually looking at another type of optimization technology, which is called robust optimization. So by its name, robust optimization actually is to optimize under the worst case of the uncertainty. So the decisions will be immune against any uncertain realizations. Okay? And in order to model the uncertain variables, instead of the PDF, the robust optimization actually use a lower and upper bound to model the uncertain parameter. So the input of this algorithm is interval prediction. For example, instead of forecast a point value, the robust optimization requires an interval value. Let's say a lower bound and the upper bound of this parameter. And it takes this parameter to optimize under the worst case of this uncertain variable. So you can see that the mathematical model here is consists of two parts. max min. The max actually is to search the worst case of the uncertainty. And the advantages of the robust optimization is it does not need the PDF because it's just a use interval to model the uncertainty. And another very important advantage is it is fully robust against any uncertain realizations. However, this comes with its disadvantages because this may be very conservative. When we consider the worst case, probably the solutions may be over conservative. So this is basically the two mainstream optimization technologies for microgrid operation problem. Okay, then next I will briefly introduce a representative work for the energy dispatch for the DERs. So this one, we are actually optimizing the so-called day-ahead price-based demand response and hourly ahead microturbine output dispatch. So the price-based demand response, the principle is that the utility company want to use the price signal as a control measure to adjust the user's load profile. So basically, the higher electricity price, the lower power demand it will be. There is a negative relationship between the two. And this relationship can be modeled by the so-called price elasticity, okay? And so according to some literature study, this price elasticity is negative 0.83 for Australian power system. While for Singapore power system, we are actually asking our master students to do a comprehensive survey to study this parameter. So based on this price elasticity, you can see that originally when the price is 100%, the original level, we have 100% load level. While the electricity price increased by 10%, you can see the load will decrease by 2%. And reversely, if the electricity price reduced by 10%, the load will increase by 2.3%. Okay, so this is a so-called linear negative relationship between the two. And okay, based on the electricity price, the utility company can send, they can decide the day ahead the price value and send this price signal to the customer in a day ahead time framework. Then after receiving this electricity price, the customers will adjust their load demand. And by doing this, the whole utility company can achieve the load shifting or peak shaving purposes. So this is a general principle for price-based demand response. And okay, in our research work, we want to, as we can see that the price-based demand response is actually implemented in a day-ahead time frame. However, during the intraday time frame, we still need to balance the total demand and the total generation. So here in the microgrid, we can dispatch another flexible resources. In this case, we consider the microturbine, which has a relatively faster responding speed. So under a two-stage coordinated framework, in the first stage, we optimize the price-based signal for the demand response. And in the intraday, the second stage, we hourly dispatch the microturbine. So the two stages are coordinated through the robust optimization model, which is briefly modeled here. And the total objective function is actually to maximize the revenue of the microgrid operator, which is equivalent to minimizing the negative value of the profit. So they are mathematically equivalent. And in terms of the uncertain variables, we consider the solar PV, wind turbine, the power output, and we define their lower bound and the upper bound to model their uncertain variation. And besides, we also model the demand response uncertainty, because not all of the customers will respond to the price signal, because some customers, they may not be sensitive to the price signals. They will continue to use the electricity, no matter how the electricity price changes. So this type of uncertainty is also modeled here. And after that, we also need to ensure that this price-based demand response does not affect the customer's benefit, which means that after they take this price-based demand response, their total electricity bill should not be increased. And their access to the electricity should not be affected as well. So this type of constraints should also be well modeled. And then in this figure, you can see some of the simulation results. This figure is the prediction of the interval prediction of the load, the wind power, as well as the solar PV output. And this figure shows the simulation results. The blue curve is the one is the load curve without the demand response, and the red curve is the one after the response. So as you can observe, in the noon time, especially when the solar PV is producing a large amount of power, we are actually encouraging the customer to use more power. Okay, and during the evening time, when there is less solar power, we are actually disencouraging the customers to use power. Okay, so in this case, we can maximize our utilization of the renewable power. And we also compare our robust optimization method with other considering different uncertainty levels. And you can see that for different uncertainty levels, the proposed algorithm can achieve a very good robustness under the uncertainty. And this work has been published in this paper 3 years ago, and it has been listed as a highly cited paper since then. Okay, then the second operation problem is on the voltage regulation. Because as we know, for the low voltage distribution networks, the resistance to reactance ratio is much higher than the high voltage transmission network. That means the active power fluctuation from the renewable energy resources will also affect the voltage magnitude of the distribution network. So when the solar and the wind power are always fluctuating, the voltage magnitude will also fluctuate as well. While the traditional voltage regulation devices, such as the capacitor banks, transformer tap changers, they are mechanical equipment. They cannot respond fast enough to this voltage fluctuation. So another, okay, on the other hand, as I mentioned earlier, the solar PV power converters as a power electronic device, they actually have the reactive power support capacity. So idea here is to utilize the power converter of these solar PV renewable energy resources to provide the reactive power support as well. And we want to combine these power converters with the traditional mechanical devices, capacitor bank and OLTC together to coordinately support the voltage of the grid. So following the same operational, two-stage operational framework, in the first stage, we are dispatching the mechanical devices, capacitor bank and OLTCs. And in the second stage, we dispatch the power converters of the solar PV. And the two stages can coordinate it through a stochastic programming approach. And okay, in terms of the mathematical modeling, we minimize the total power loss of the network, expected power loss of the network for the operational intervals. And we consider different random scenarios of the renewable power output as well as the load variation. And after that, after some mathematical operation, we convert the whole problem into a deterministic optimization problem, which can be easily solved. And here I can show you some of the simulation results. The first figure is the power loss of the whole day, 24 hours. This is our optimization objective. We are minimizing total power loss. And the second figure is the results for the transformer tap positions. And third figure is the position of the capacitor bank. So as you can see, for these mechanical devices, their status do not change much for the whole day, especially for the capacitor banks. Because most of the reactive power support come from the solar PV inverters, which is shown here. For this one, the time interval is 15 minutes. So you can see that within every 15 minutes interval, the solar power converters are injecting or absorbing the reactive power. So the whole voltage of the network can be managed. And these two figures show you the voltage magnitude of two buses. You can see that they can satisfy the operational limits, which is plus minus 0.05 per unit. Okay, so this is another work for the voltage regulation problem in the microgrid operation. Then in the third part, I will talk about briefly talk about the planning of the DER units in the microgrid. So generally speaking, the planning problem is actually a portfolio decision-making problem. The objective is to select the right type of the DER units, to size and locate the units, as well as to design the investment timeline, taking into consideration of the distribution network model, uncertainties of the renewables, power output, load demand, as well as the model and the characteristic of the DER units themselves. So in this work, we basically consider two types of the DER units, including the distributed generators and as well as energy storage systems. Then the whole problem is modeled as an optimization problem to minimize the total investment cost, taking into consideration of different constraints, and to decide the size, site, type, installation year, etc. And because we also have uncertainties for this problem, for short-term operational uncertainty to long-term planning uncertainties, so we also apply the stochastic and the robust optimization algorithms for this study. The first one I would like to introduce is on the distributed generator planning. So here we consider different types of distributed generator units, including the dispatchable diesel generators, as well as a non-dispatchable solar PV and wind turbine into the microgrid system. So this is a compact form of the mathematical model, and the whole problem is formulated in a so-called embedded two-stage optimization problem. Then I can introduce you the planning results, as you can see here in this table. So we define 3 years as one phase. So totally we are considering 4 years as a phase. So totally we are considering 12 years of the planning time horizon. Then for different buses of the system, the results show you how do we place and size the different units, including the CCHP unit and the other thermal units, electrical boiler, solar PV, wind turbine for different buses and for different phases. So objective is to minimize the total investment cost plus the expected operational cost. Okay, then after distributed generator planning, we also did some work for energy storage system units planning. So here we actually consider a multi-energy system, considering both electric system as well as the thermal system. So for this work, we also need to model the thermal load of a residential building because we want to provide the district cooling for the customers. So the total, the energy storage system consider both battery electric energy storage system as well as the thermal electrical system, energy storage system. So for this distribution system, it can be divided into 3 thermal groups, which take the district cooling for their cooling demand. And this is the planning results. Again, we have 3 years for each phase. We are looking at a 9 years time horizon for different buses. This is the result for the battery energy storage for their capacity. And for the thermal energy storage for different groups, this is the planning results. Okay, so the above, what I have been describing is our representative works in this area. Apart from them, we have also published many other works for this topic. So if anybody is interested, you can have a look at our publications. And actually, we just completed a whole book on this topic. And this book is actually just completed and will be available from this month or early next month. This book will summarize all of our research works as well as practical projects in this area. Okay, with this, I end my presentation. Thank you very much for your attention. Thanks.
Thank you. Thank you, Professor Xu. It's very interesting topic, and thank you for you taking the time from Singapore to join us. I think the timing of all of today's topics are very timing. I was told by my Mercedes salesman that if you want to buy a electrical Mercedes in Hong Kong, you have to register, prepay deposit, and wait for at least 2 more years before you can see your car. So the line is very long. But then at the same time, Hong Kong already announced that after 2035, they're not going to issue another car license for a petrol fueled car anymore. So I think that brings us to the third speaker of today, Dr. Andrew Wu Yang will talk about evolutionary policy incentives for sustainable development of electric vehicle. I couldn't think of a better timing for such a topic. Dr. Andrew Wu is a lecturer in the Division of Science, Engineering, and Health Studies of Polytechnic University, SPEED, S-P-E-E-D. His research interests include an energy market, public policy, electric vehicles, and renewable energy. He is here physically today, so he will speak from the lecturer's platform here on site. Dr. Wu received his Master of Science and PhD degrees in electrical engineering, both from the Hong Kong Polytechnic University. He also has a Master of Science degree in Global Finance, jointly from Hong Kong University of Science and Technology and the New York University. Since I'm also a graduate of New York University, so I am very happy to introduce a much younger New York University alumni as a speaker for today. He is truly a person with multiple talent. In addition to his academic qualification in the science and engineering and health area, he is also a chartered financial risk manager and a full member of the Hong Kong Security and Investment Institute, MESA, as well as the Institution of Engineering and Technology. So without further ado, Dr. Wu.
Okay, thank you very much, Chairman. Please allow me to show the PowerPoint with all the audience, both in this lecture hall and also online. Thank you very much, Chairman. It is really a great honor for me to be here to share with you some of my recent work related with the policy incentives, especially for the electric vehicles industry in the China, and actually Chinese mainland to be more specific. So today I will go mainly through 3 topics. So first of all, I will share with you what is the evolve of the policy mechanisms for the electric vehicle industry in China. And actually, China has been started to promote the electric vehicles decades ago. And however, the policy at the first stage might not appear at a very strong incentive. And in the later stage, the outcome, we know that it is very good. And we would like to find out what is the reason behind and what is the hints for us to improve our achievement in the future. So recently, the policy incentives has been strengthened. And as a result, some of the financial subsidies has been slowing down. This is not a negative signal. On the contrary, it proves that the performance of the promotion of electric vehicle has been achieved a very fruitful and sound result. And that's why they can gradually slow down and move on to the next era. So first of all, I'd like to share with you some of my findings, summarized from a journal article that we just published earlier this year in the Q1 journal with impact factor 5.2. So generally, the initiation of the policy incentives to promote electric vehicle in China has been started in the year roughly in late 2008 and early 2009. And at the very beginning, the tentative to propose such initiation in only several cities as a pilot and demonstration project. And after that, after 1 year, in 2010, the financial subsidy came. So really, we have some benefits for the commercial users and for the manufacturers. With the sound proof, by the end of 2012, we move on to the next stage. In 2013, we expanded the demonstration and pilot projects to more provinces and more regions in the Chinese mainland. And in fact, from 2010 to 2013, the financial subsidies has significantly increased. And as a result, as we can see, let's take the Greater Bay Area as an example. Shenzhen could serve as a very good example for Hong Kong and Macau in terms of the promotion of the electric vehicles, especially in the public transportation sector. And if you've visited Shenzhen, maybe just before the pandemic, you might realize that over 95% of the taxi in Shenzhen has already been electric taxis. So electric taxi and electric bus might be the kickoff for Hong Kong and Macau's consideration in the near future, in the next several years. And as you may know that the Environmental Bureau of Hong Kong government has just announced the public policy in April this year. And one clause in the policy mentioned that by the end of 2035, there will be no new registration of conventional passenger cars. So we are also trying to promote more electric vehicles as possible. Well, let's come back to this PowerPoint. And starting from 2016, we start a recent phase 3. And we promote further the policy incentives from those provinces and regions to the whole Chinese mainland. No matter which city you are, no matter which area you live, you will enjoy such financial subsidies. And however, later we will mention that the areas, the regions has been expanded, but the single subsidy for one applicant slightly dropped. And we summarized some of the key national level policies in the recent years, only in the recent years. You may refer to the full table in my journal article. All right. So as we can see that starting from the year 2016 to the year 2019, we can see that the financial subsidy for a single applicant actually dropped a little bit. However, the expansion, the area has been expanded. All right. So due to the time limit, maybe please allow me to move on to the next page. And we'll see that there are two ways. Okay. There are two ways we can promote electric vehicles. One way is to improve the use of electric vehicle. And the other way is about to reduce the use of conventional cars. And that's why the national level policy proposed a dual credit regime. And when we say dual credit regime, one regime channel is on the increase of electric vehicles. And the other regime is about how to slightly reduce or gradually control the use of conventional vehicles. And here the CAFC, a corporate average fuel consumption credit channel, is about the control and constraint of the use and manufacture of conventional vehicles. And I may not jump into the detail of this mathematical model and the formula. However, I'd like to point out the result and the purpose of this regime channel here. The CAFC credit, it can generate either a positive number or a negative number. If the result is a negative number, it means that this manufacturing company need to try to use his reserved credit from the previous year, or need to purchase the extra credit from the other companies who obtain a positive result in this year. So which means it serves like a pool. So actually it gives us a lot of imagination that this might grow into like a carbon trading platform in the future, but we don't know yet. But technically they have such technical elements and financial foundations here. There is a reserved pool, there's buyers and sellers, and there could be some trading here under a strict regulation. The other regime, as we just mentioned, is about the promotion of the electric vehicles. So this regime channel is called the New Energy Vehicle, NEV credit. And the purpose of this credit channel is to provide more incentive for the manufacturers to manufacture more electric vehicles. And when I talked with the scholars from overseas, some of them have the concern that how about the quality of the electric vehicle? And we know that China has a long history manufacturing electric vehicles, but some of them are of the top class quality, some of them might not. But no worry about this, because if we refer to the detail of the policy, they have a very specific and accurate definition on the technical specifications, including the type of the battery, including the control system, including the driving cruise, the cruise range, etc., etc. And even for the nature of the battery. So again, the purpose of this NEV credit is like a pool as well, like the CAFC credits. So if the company make or manufacture more electric vehicles, they will get more credit for them to sell or try to seek for extra gain in this financial year. So the electric vehicle manufacturers will have the financial income in two aspects. One aspect is about the manufacturing of electric vehicles, sales of electric vehicles, and on the other side, they can also sell the credits that they gain through their manufacture To whom? To those who get a negative number on the CAFC credit. All right. So I summarized the automobile enterprises extracted table in the year of 2019. I'm still waiting for the source to update the number of the year 2020, but due to the pandemic, some of the information disclosure is kind of a little bit delayed. But I believe they will update their numbers very soon in the near future. So you may see that the Tesla Shanghai is highlighted in red and the number is relatively small. And the reason is Tesla Shanghai was just opened in late 2019. So therefore, they only manufacture for a few months at that moment when this table is summarized. All right. So we can have the CFC credits and NEV credit here, as you can show. And some of the companies generate a positive number, and some of the companies generate a negative number. Who generates the negative number need to purchase the extra credit from the positive numbers. All right. So based on the previous table, we forecast the estimated EV production in the next few years. Let me just tell you the result of the charts. So because there is a dual credit regime, so I categorized the forecast of the EV production also in two regimes, following two regimes. One is the CFC only, and the other is the NEV only. So as you can see, the red part and the red bar represent for the CFC credits. It means that if the company would like to achieve to the balance, so the whole industry as a whole, there is no surplus or no deficit. As a whole, there is a balance. And there is a kind of a predetermined growth rate as per requested and required by the national level regulation authority. Like the MIIT and the Ministry of Finance and also the State Council, etc., etc. So there is a predetermined target of the growth rate of reducing the conventional car and increase of the electric vehicles. So if we consider the balance of CFC only, you will find the estimation of the forecast EV production in the red bar. If we consider the NEV credit channel only, we will find out the estimation of the EV production in the blue bar. Because the paper was published earlier this year, so there will be an update number. I hope that I could have another opportunity to come again and give you the update number after 1 or 2 years. So based on different scenarios, especially if we consider the challenge and the negative impact brought by the pandemic, as we knew that some of the factories and the supply chain has been delayed, and some of the manufacturing work has been suspended. So we have the negative growth scenario here. So they're kind of brought a challenge for the electric vehicles industry in China to achieve their targets as required by the national level authority. Of course, one of the reasons is due to the pandemic, and we didn't foresee that in the year 2019. So there is some possible solutions that we can make up and try to cross over this challenge. So we also propose some of the policy implications in our journal article. So for example, we encourage the ongoing development of market-based green financing in China, which will provide an alternative source of a low-cost funding for the further development of the EV sector. Because financially, there is one constraint for the EV manufacturers. And we know that due to the pandemic, the chips specifically designed and used for the automobiles has been short of stock globally. And you may also read from the news that China is actively trying to research and develop and promote its own technology on the chips, not only on the automobiles, but also on the other UNVs. And also we propose the attempt and challenges for turning from a policy-driven to a market-driven industry, which matches what I mentioned about the CFC credit and NEV credit to form early stage trading platform to provide market-driven incentives for the factories and market players to improve their technology and to invest and allocate more resources in the electric vehicles manufacturing and the use. So I believe that should be all about what we talked about in the journal article. So do we have any questions, or you'd like to have something to interact with me?
Okay. Okay, yeah. Okay, thank you, Dr. Wu. Thank you for a very good and informative presentation. As Connor mentioned earlier, he has to leave earlier because of a prior engagement. So the next panel discussion would be hosted by myself and my colleague, Ivan. Okay. Like Colin mentioned earlier, all three presentations are very informative and very interesting, very different angles. Some talk about the hardware, some talk about the policies, some talking about the incentives, more specific details, right? So, but I think I noticed one thing is very interesting is that there's a lot of different stakeholders working together, not only the science, but the government, the policies, and to very specific incentives being implemented and tried out, but all with the same aim of achieving what I call a better use of the energy, which is the mandate for HAESCO anyway, right? Because we're aiming to promote the energy efficiency, and so that no energy is wasted. But in different aspects, we're all working towards the same goal. And the timing, as we all notice, is actually very timely, okay? As Colin also mentioned earlier on, not to mention the COP26 just completed in Edinburgh, and the consensus being built up around the world that we need to do something to help the environment. So I again thank all the speakers, Dr. Li, Professor Xu, and Dr. Wu for giving us a very interesting talk today. Now, this next session is actually about the panel discussion, and essentially we would invite the three speakers, the two online, to join us, and Dr. Wu would be with us physically. And then we invite all participants to ask any questions. I believe online there's a function that
you can pose questions, right? So we can read from your questions and then try to answer them. Okay. Perhaps I don't know, Ivan, you have any question?
Maybe the floor first, or maybe we also both invite the Harry and Dr. Shi to turn on their camera first, and then we can have a live discussion. Yeah, thank you, Professor Shi. How about Harry, Dr. Ni?
Hello. Yeah.
Okay, thank you. Rob, can you help us to maybe arrange the screen so that we can see it all? Yep. Okay, so it's very interesting discussion today. Yeah, because like Dr. Ni mentioned from the supply part, from the power market supply part for the virtual plant, how to use the virtual power plant technology to increase the efficiency, and also use to adopting like a market incentive to promote the higher efficiency and also the lower cost, those kind of a efficient operation in the power market. And for Dr. Shi mentioned that how to use the technology, also including machine learning and also lots of different kinds of optimization strategy to to coordinate different kinds of resources. And Dr. Wu, Andrew mentioned from the demand side how to promote the use of the EV, so I can see a full life cycle. And I want to ask a question for all of three of you, how you see some maybe some cooperation opportunity among the speakers, because I see there's a lot of synergy and also maybe there's some overlap point. For example, from my point of view, I can see, for example, the VPP, the framework proposed by Harry, maybe can have some, also can work together with Professor Shi in his proposed DER coordination framework, right? And like what Dr. Wu mentioned, the EV, like Dr. Shi already mentioned in his DER, the EV can also like support as one of the, not only the producer, but also a consumer. So I think quite funny from three of you. So who's gonna be the first? Who's gonna be the first?
I maybe this is Harry, and let me start. Just I really glad to hear what you said and your proposal to bridge us together. Actually, I think you're right. The VPP is based on the large amount of existing resources, especially from the residential and the customer power consumers, like the ACs or water heaters or others. They really we kind of somehow we out of our side or radar to control the power grid or for the smart grid for a long time, but really now kind of driven by the power market and also the 30-60 targets become so important and become even getting closer to the center of the stage. So if our solution could be somehow kind of piloted on the Dr. Shi's the beautiful line island, the beautiful project, that'd be great. And we really want to try how to integrate some resource to be part of the dispatchable resource by Dr. Shi's project. So that'll be the microgrid also need VPP, I think.
Okay, yes, I think it's my turn. Yeah, I really appreciate Dr. Li to raise this question. I fully agree with Dr. Li's point. There are definitely potential for collaboration because these concepts have certain synergies. My understanding of VPP is that for VPP, we are aggregating the resources virtually, which means they do not necessarily to stay in one physical location. So for our research, we are actually looking at the resources within one physical microgrid. But essentially, the algorithm, the optimization, aggregation algorithm, they are quite similar. Yeah, so I think maybe after this workshop offline, we can have more discussions to see how we can maybe collaborate on these topics. For our projects in Singapore, yes, there are a lot of potentials for these software companies or even hardware companies to get involved. Yeah, thank you very much.
Thank you very much. I definitely, yeah, and I definitely believe that both Harry and Yan are the senior fellows that I should learn to. And truly, there are some research collaboration between different institutions and different scholars. And so far, me and my team, we are holding 4 research projects, and 2 from PolyU internal, and 2 from the Hong Kong government Research Grant Council. And one of the projects that I can think of the possibility of future collaboration is about the, also is related with electric vehicles, and actually it's about the optimized mapping of the charging facilities for the electric vehicles, electric taxis, both for the public transportation sector and the private transportation sector in Hong Kong. And we may select a pilot region in Hong Kong, either a small area in Kolo or in New Territory as a test point to see if we are really promote enormous number of electric vehicles by the end of 2035. And there is a lack or a lag of the charging facilities nowadays. So as you may also know that Hong Kong is actually a very crowded and congested place. So there are a lot of limitations and constraints for us to plan and place those newly built centralized or distributed charging facilities in Hong Kong. So such optimization problem, together with the traffic network challenge, as well as other financial constraints and risk management constraints, I believe that could be a very perfect topic for me to co-work with Yan and Harry together. And I think I will have a lot of questions to ask them too when I started the project. Thank you.
You're welcome. And I think we're really looking forward to visit your research team once after the border reopened between the mainland and Hong Kong. And hopefully we can have a deeper collaboration, not only in how to apply the technology in Hong Kong, but also in a lot of the Chinese local, there's some crowded cities in China too.
Thank you. I think we all look forward to the opening of the border. I do have a question. I do have a question for actually all 3 speakers, because they, like we mentioned, your topics are all from a different angle, but with the same objective. And the objective is to help to use the energy more efficiently so that we would have a climate impact, reduction of the CO2, the greenhouse gas, right? But slightly different angle. So may I perhaps ask each of you in a summarized way? I know there's a lot of details involved. How do you think your technology, your endeavor would help to achieve that goal? Maybe you can quantify it. For example, in the case of Harry, we talk about the VPP. Okay.
Yeah.
And all these market mechanism, how the government is supporting it. But what's the end game in the carbon reduction? In helping China achieve that. And likewise to the other 2 speakers afterwards. Maybe Harry, you can go first.
Yeah, sure. Thank you very much. This is really excellent questions. And like we just we kind of kick our pilots in China, in some of the Chinese cities like the like the Hangzhou, like the Ningbo, like the Guangzhou. And according to our pilots, not the even the amount is not that the number of the units we installed not that many, but we after our research with the Zhejiang Energy Department Department of Energy, and we basically got gave you some very brief some numbers that related to the CO2 or the greenhouse gas equivalent reduction. If we can use about like the half of the Hangzhou city's air conditioners, like the mini splits, That's about like the if we can use them and integrate into virtual power plants to help the more renewables to be used by the grid. And we basically see the annually the CO2 equivalent greenhouse gas reduction will be 4 million tons, and that's for AC only. And if we can integrate water heater, that will be triple the number, will be 12 million tons of the CO2 emission reduction for Hangzhou City, and that's for the Hangzhou City. And if we look into the Chinese map, there you can see about like the other about like the 60 to 70 cities, even not the same size but close to Hangzhou, and we will see like the if we can really explore all the great potential from the VPPs just based on AC and water heater, we will see the contribution of the 2 to 3% of the emission reduction for the state level. And if you can imagine, that's all just the using the existing kind of the existing resources instead of like the large amount of investment to build the incremental resources. So that's what we believe should be the first step, and for most of our Chinese mainland cities, and also to achieve their 30-60 targets.
Okay. From my side, in the local Singapore's context, here over 95% of the electricity is generated by natural gas power plant. So the government actually has set a very ambitious goal for the solar PV uptake, because as I mentioned, we actually do not have wind resources here. So instead, we are looking at the solar PV. So if I remember correctly, the estimation numbers for the solar PV uptake will be by 2030, that will be how much? 1.5 gigawatt peak. And by 2050, that will be 2.5 gigawatt peak for the solar PV capacity. So I think for our research project, actually, the efforts is actually to develop the advanced energy management system for the whole power grid to integrate these highly uncertain and stochastic resources. And by doing that, we can definitely achieve the carbon emission reduction. Yeah, so that is basically some information from my side. Thanks.
Oh, thank you very much, Harry and Yan. And it reminds me that in the year of 2014, the Hong Kong government announced a public consultation document in terms of the fuel mix of Hong Kong, both locally nowadays and in the future. And I happened to work in the Hong Kong Electric in that year. And as a result, the government authorities, together with various stakeholders in Hong Kong, we propose a future fuel mix in terms of how many percentage we will use for electricity generation by natural gas, and how many percentage by coal, and how many percentage of the renewable energies. And the ultimate goal is to reduce, first of all, to reduce the use of coal and replace it with more natural gas, which we all know that in terms of the carbon neutralization, the carbon emission of using natural gas is much cleaner than the use of coal. And also, we'll keep doing the purchase of the nuclear power from Guangdong province in terms of to reduce the carbon. And that is on the source of the electricity generation. And in the demand side, we'll try to promote more electric vehicles to reduce the roadside carbon emission and the roadside air pollution. So I believe there is both ways that we can do in Hong Kong locally in the next several years.
Thank you to all three speakers. Perhaps before we talk among ourselves, let me ask: is there any people posting questions online? You're free, and encouraged to do so if you have any questions. And I also can ask the audience in person. Okay, perhaps we can pass a mic.
Thank you. I just wanted to ask, particularly on the vehicle side, you talked about the new energy vehicle scheme. Does that only apply to electrical vehicles, or would that also apply to fuel cells, to hydrogen vehicles? And we talk a lot there about microgrids and generators into microgrids. So a second question really is about the adoption of fuel cells. It's been a very slow adoption. And are there any barriers that you see in the adoption of fuel cells, or what role do you see them playing in the future in these microgrids?
Yeah, I'll take it because it's specifically the question on my side. So you are correct about the slow adoption of the fuel cell and the hydrogen car in China. The answer for the first question is the NEV credit channel is specifically designed for the electric vehicles only. So far, the fuel cell car and hydrogen car was not involved in this policy paper, but they are involved in other policy papers, which we didn't discuss today. And I could see, or personally, I foresee the there is now the active research and development on the hydrogen technology nowadays. There is already an active investment and allocation of the resources, both financially and on the manpower of our own technology for the hydrogen cars. In terms of the public use, especially for the public transportation, the amount is not as comparable as the conventional cars using gasoline, or even compared to the electric vehicles. There are various reasons behind. Both from the policy side and from the financial side, we could say that the financial incentive is not as strong as enough, and the manufacturers simply do not have a sufficient financial profit to drive them to go that way. And also in the past decades, the technology of hydrogen and the application of the fuel cell has some physical constraints. And as a result, the promotion is not as high as the other types of cars. But personally, I believe that in the future, there will be more alternative choices, especially for the use of fuel cell and the hydrogen automobiles. Thank you.
Maybe I got one more last question for Dr. Xu. Because you mentioned like the coordination of different distributed energy resources. And from my point of view, a lot of the people just claim that the renewable energy is not so stable. And because due to its intermittency, not the supply of the renewable energy sources is not stable, not constant, or maybe not controllable. But from my point of view, I think this is a dynamic process. when now the percentage of the renewable, the penetration only like less than 10%, is just like what people maybe say correctly is like unstable. But when it's like 40%, maybe it's a high risk for the power grid for due to its highly intermittency. But what I want to say is that like the Earth is turning all around, and always we actually have a 1/3 of the ground is covered as enjoying the sunshine. So how about if the penetration of the percentage of the renewable sources, like for example the solar panel you mentioned today, is high enough? The number is greatly enough. So is it possible that the grid can connect to international level, so that always we have a 1/3 of the power supply from the solar panel, and then can support the world. So at this stage, maybe some years later, when the percentage of the renewable energy sources is high enough, is it possible to becoming a so-called mature or stable resources? So I just want to hear some of you from the point of view from you that with the keywords today of the coordination. Okay, thank you, Professor Shi.
Thank you. Thank you, Dr. Lee, for this question. Yes, I think theoretically speaking, definitely it's possible to interconnect with different continents, different regions of the world to enjoy the solar power. But practically, that will create a lot of technical questions. For example, how do we interconnect these power grids? Because we need to have the infrastructure. We need to have the, let's say, high voltage transmission grid to get these countries interconnected. And besides, when we connected these countries as together, when we practically operate the power grid, we also need to have certain power reserve for the one grid. Let's say if the solar power suddenly reduce, we need to have our reserve power for the, importing grid. So that means there will be a lot of technical questions. However, I do see there are a lot of plans or proposals for different countries on this so-called global energy interconnection. As far as I know, in China, we have a so-called Global Energy Interconnection Research Institute. They are actually proposing this so-called Global Energy Internet. And I also know that in China, we have very advanced high voltage transmission technology, HVAC or HVDC, very advanced. So theoretically, I think it's definitely possible. But then practically, I think we need to solve a lot of technical questions. Well, for the Singapore's context, actually just several months ago, the local government has announced several power import plan to take the power input from the neighboring country, Malaysia and Indonesia. And as far as I know, there is even a very ambitious so-called commercial proposal that is to build up a solar PV in Australia, then transmit this solar power through Indonesia to Singapore. That is a very so-called very promising plan, and which is actually under discussion. And I see already some of the companies have already set up to do this business. Yeah, so I think this will be a very promising plan in the future. That is to connect the countries internationally. Yes, thank you.
Thank you, Yan. I think it's certainly something that it would take many years, I believe, to achieve. Okay, but I think one thing to note is really I have a strong impression that they are ultimately the same goal, but different timeline, right? Some can be achieved quicker than the others. Some may be longer range. And then right now, collectively, we are allocating resources, if you will, sharing knowledge, allocating resources to make that happen. And I'm excited today that we talk about a couple of areas that we are very definitive, very concrete steps that we're taking. For example, the EV penetration in China is huge, right? You mentioned, Dr. Wu mentioned about the Shenzhen taxi, right? And we're seeing that right now in Hong Kong. Hong Kong right now is having the first international car exhibition. So if you go there, you will notice that essentially all major brands, they have the EV lineup. I know Colin talked about waiting 2 years for his Mercedes, But if you want to have a BYD, I'm sure the wait is a lot shorter. Okay, so but you can see that these are very near term, immediate. And then we heard about Harry, the VPP. They are already conducting the pilot cases, and already 8 provinces. They are doing something in different stages, albeit, but they're doing something to make that happen. Now, I don't know what's the so-called the end game as to when that would be fully implemented, but you can clearly see that the resources and the policy are supporting that. And we also heard from Yan that the government is supporting this research on the microgrid so that they can increase on the renewable. So to us, it's actually very exciting, because I think we see this public awareness is being risen and people are collectively doing something about it. And I don't know whether there are any other questions from the online. If not, I think I would like to end on that note, leaving us some thought in our mind, some questions in our mind. And I think we all would find time to chew on it. And then maybe we can have further synergy that we talked about, cooperation, to make it happen, because we all have a role in it. Okay, and I would like to thank all the speakers again for taking the time on the Saturday morning, and all the supporting organization and all the team to make it a very good event. Thank you so much.
Thank you.
Thank you. Thank you very much.
Thank you. Thank you.
Okay.
See you next time.
Thank you. Thank you.
See you.
Bye bye.
See you. Bye.
Bye bye. Thank you. Bye bye.